Okay, so let's go on. Let me introduce you the next speaker, Dr. Jayneel Parekh. He's currently a postdoctoral researcher at Sorbonne University working on understanding representation in large multimodal models. He completed his PhD at Telecom Paris, studying interpretability in deep networks for image and audio classification. His work on audio interpretability has been recognized by Université Paris-Calais and Institut Polytechnique de Paris with second prize for Beck's doctoral project 2023. He contributed to the field of explainable AI with papers such as Flint and L2I, and today we'll discuss a novel interpreter design incorporating non-negative matrix factorization.
Thanks for the introduction, Francisco. I hope everyone can hear me and see my screen. Could you just...
Yeah, everything is fine. Yeah.
Okay. Yeah, thanks for the intro. So the title for the talk today is Tackling Interpretability Problems for Audio Classification Networks with NMF. And this work was done as part of my PhD at Telecom. Before I start, I just want to thank my collaborators and co-authors, Sanjeel, Pablo, Florence, and Gail. Without their support and contributions, this work wouldn't be possible. So I want to start by just giving a brief intro about the field. Although I believe after all the talks today, this is probably not, people might already be used to it. So I'll be fast with this. So I begin by first making this observation that machine learning or AI algorithms are increasingly being employed in places where they highly influence the human experience. So just as an example, they might be used as trading bots or used to make decisions for a self-driving car. But the point to note here is that these models are still prone to errors, and their errors can have catastrophic consequences. So if because of some spurious feature detection, a bot starts to buy high and sell low, it can completely destroy a trading firm. So the underlying point is that we can't blindly trust these models. We need to have some level of understanding of how they're making their decisions. And this precisely leads to interpretability. So what is interpretability? The definition that I'll adhere to, which is, I think, fairly common, it's that it's the ability to gain human understandable insights about a decision process. And then you might ask, why should we study interpretability? So there are multiple reasons for this. Obviously, the social and legal requirements might force a company to provide some level of understanding about their models. But beyond that, it can be a great building block for human AI decision-making systems. Interpretation as a signal can be very useful to improve aspects of a model, maybe its robustness, performance, etc. It's a great analysis tool to understand the structure in your problem, gain more understanding about your model. And even beyond all these aspects, there is always this innate human curiosity where we always want to understand the systems around us. So till the time we're using these systems, we'll always be interested in understanding them. There are particularly two types of problems interpretability is generally interested in or centered around. So the first is the post hoc interpretation problem. So we are given a fixed pre-trained model, and we are supposed to devise an external algorithm to gain understanding about its decisions. Now, the version of the problem, I'm making certain assumptions, which I'll stick to for this talk. So I'll assume that we have an audio input, which is being processed as a spectrogram-like representation by a CNN for some classification task. Now, probably some of these assumptions could be relaxed, but I think it's better to stick with them, at least for the work I'll present. And the second type of problem that people are interested in is this by design interpretation problem, where we're supposed to train one single model that can do both classification as well as provide interpretation. So the network by design needs to be interpretable and have high prediction performance. So these will be the two problems we are interested in, and we basically developed a framework to address both of them. And I'll give the motivation behind our framework. So imagine there is an audio scene. So there are multiple different sources. Maybe a dog is barking, vacuum cleaner is operating, so on. And there's a microphone which records all the sounds, and it sends to a emergency event detector. And suppose the detector sends an alert on your phone that a smoke alarm went off. If at a later stage you want to confirm, was it really some smoke alarm that led to the alert? You would defer to the interpreter. And an ideal interpreter, we believe, would be able to represent different audio objects that compose a scene, and it would be able to make the interpretations listenable to the user so that it eases the process, because it's hard to understand just visual saliency or importance maps. So these are our two expectations from the interpreter. And most existing interpreters, at least at the time that we were working on this, uh, and I would still say most, not all, they've failed on at least one of these 2 points. They would either not be able to effectively represent the audio objects in the input, or they won't be able to provide listenable interpretations. Because yeah, spectral visual attribution maps, they're typically not understandable for most users. And we also found it non-trivial, at least qualitatively, to use those attribution maps as filters, at least in most cases. Uh, at this point, I would just like to make a note that providing listenable interpretations, it's not the same as source separation or denoising tasks, particularly because in these classical tasks, we are interested in separating out a complete object of interest, a source of interest. But that need not be the case with interpretations, because a model need not focus on all the parts of the object we are interested in, maybe only on selected parts, certain salient regions. Our hypothesis was that uh, we we need to go for a different representation to generate our interpretations that can satisfy both of these requirements. And our answer for it was in NMF. So what is NMF? So NMF is non-negative matrix factorization. I assume that probably most of you are already well aware of it. But if someone does not know, I'll just give a brief uh, intro. So NMF is non-negative matrix factorization. And what it does, it's a matrix decomposition technique. And it decomposes non-negative matrices as product of two low-rank non-negative matrices. So if we have a magnitude spectrogram V, it decomposes it as a product of W and H. Both have the rank K. This K is typically smaller than both F and T, the frequency bins or the shape of V. The columns of W are the basis vectors, also referred to as components or maybe spectral patterns. So these are essentially like the frequency fingerprints for this input spectrogram. And the rows of H represent the time activations of the corresponding basis vectors or components. Why or how do we want to use NMF? So there are two reasons for this. There are variants of NMF where you can learn one single dictionary to model all the audio objects in your data. And this is the more direct reason. There's an indirect reason that this decomposition structure in NMF, it heavily inspires our design of the interpreter, which I'll describe next. So I'll present the framework which can address both post hoc and by design interpretation. I'll start with the post hoc interpretation problem, and we'll find a very natural extension for by design interpretation. So for post hoc interpretation, we have our classifier F, the audio processing CNN, and that we wish to interpret. So it has hidden layers F1, F2, F3, so on. It's processing this X, which is some spectrogram like signal, and its output is f of X, the whatever classification it's making. The interpreter, it's implemented as a neural network, and there are certain key things that I want to emphasize for its design. The first is that it has access to certain hidden layers of the classifier. These hidden layers are typically selected from close to the output layer. It processes them, processes those hidden representations through a function psi, and outputs an embedding, which I'm calling right now hi of x. The whole framework is built around trying to learn to predict this embedding so that it satisfies whatever we require from it. So we require it to interpret the decision f of x, as well as fulfill the interpreter requirements I mentioned earlier. And the way we do that is by implementing these constraints as losses. So I'll just introduce what those losses are. The first loss is the output fidelity loss. Since we want to understand the output f of x through this is an intermediate embedding, we have this function theta, which operates on hi of x and tries to mimic f of x. So this simply shapes this intermediate embedding to understand the classifier output. But yeah, the big question is, what exactly is this intermediate embedding? So it's a non-negative matrix of size k cross t. Our goal is that we want to encode the presence or absence of all the audio objects. How? As time activations across t frames for a dictionary of spectral patterns, of k spectral patterns, W. So I'll just focus on each of these parts. So this W, the dictionary of spectral patterns, it's represented as a matrix, and it's pre-learned on the input data set. So it's already learned by the time we start this training, and it's fixed throughout. And it's representing all the various audio objects or classes present in the data. The key loss that helps us impose this meaning of time activations on our intermediate embedding is this NMF loss based on the NMF decomposition. So it requires us to approximate the input log magnitude spectrogram as product of W and hi of x. By the way, this log preserves the non-negativity. It's not log x operation, it's log 1 plus x. But the key point is that this loss is essential so that we derive this meaning of time activations from this intermediate embedding. And these are I would say, the two key losses. Now imagine if we have trained this system. Next, you might ask, how do we get the listenable interpretations? So I'll give you the brief schematic of it. So for any given input x, the theta and the time activations hi of x, they estimate the relevance of each component in our dictionary of spectral patterns. That the most important components for the decision f of x. So you estimate the relevance of each component, and then you select the most important ones based on some threshold. So imagine, suppose it's the first two components. Then because we're decomposing the original input using W and hi of x, so we can do soft masking. So we filter the input using the information of which are the most important components, perform soft masking, do the inversion, and get a listenable interpretation. Just to summarize the training of the post hoc interpretation, what are the key objects? So we start with a W, we pre-learn a W first, which is a dictionary of k vectors, k components, and it's learned by applying the sparse NMF algorithm on our input dataset. The central representation of the whole framework is this hi of x. It's an embedding which is learned from the hidden layers of our classifier, f of x, and it's learned so as to represent time activations of W. And there are basically three losses on it. The output fidelity, the input fidelity is the NMF loss, which I already described. And there's also a sparsity loss to make the time activations more sparse. The optimization objective we minimize is just a combination of these three. And it's minimized only with respect to psi and theta, which are both they're small size networks in the interpreter. Theta is actually just a pooling function and a linear length. So they have a relatively simple architecture. Now, how can we extend this? There's a very natural extension for by design interpretation. So in by design interpretation, we want an interpretable network for prediction. And since we have this interpreter function that's trying to approximate f of x, so the natural inclination is that we can use this function theta uh, acting on hi of x as an interpretable prediction network. There is one challenge though, that ideally we should not assume that f is pre-trained in this case. So you have to train all the layers of f with these losses. But again, the important thing is that we can keep all the losses for the interpretation exactly the same. So that part remains, those losses that affect the interpreter remain unchanged. We did find that adapting the layers of f for prediction most effectively, the way, I mean, there can be multiple ways to do it, but the most effective way we found was to add the a classification loss on the head f of x, even though we are not going to use f of x at the end. But that was the most effective way we found for best performance and to adapt the layers in f of x for prediction. The optimization objective, all the it's just a combination of all the losses, but you minimize also now with respect to f. So that summarizes all the training part. Moving on with the experiments to just complete the picture. We try with multiple data sets, multi-class classification data, environmental sound classification, and there are two tasks for multi-label classification. So Sounds of New York City, it's an urban sound tagging dataset, and Open Mic 2018, it's a music instrument tagging dataset. The underlying architecture of F that we use, it's a VGG style network, which was pre-trained on audio set. For post hoc interpretation, we fine tune it on each task before we interpret it. And yeah, for by design, we train it simultaneously. Uh, I mean, just for completeness, it does have a strong classification performance, although it's not state of the art, but it's definitely better than quite better quite some margin compared to the standard CNN baselines. There are multiple experiments, but they'll be, I mean, I'll focus on only two quantitative experiments. There are multiple evaluation axes, but I'll only focus on two quantitative experiments. So first is the faithfulness, which is more, I would say, more common or more popular for post hoc interpretation problems. It asks the question that does the classifier, which in this case would be f of x, it's post hoc interpretation, does it truly rely on the features that were identified as relevant by the interpretation algorithm? Now, for saliency maps, typically the way it's computed is that you simulate the feature removal process from the input. So you remove the most important features and you see how the out and you make a metric out of how by observing how the output of the classifier changes from the old to the new sample. And typically, it's hard for these concept-based methods that are not generating the importances directly on the input features. So we generate the importances on the components. Uh, However, because of this decomposition structure we have, it it does allow this possibility. And I would say in generally for generative models, it's some version of it can definitely be evaluated. The way we would do that in our case is that given any x, first we identify what we consider as relevant components. So we compute a notion of local relevance and importance of each concept, each component for a given x. We threshold the relevance and identify the set of most important components. And then we can just remove those components from the input by just removing their contribution from the decomposition and doing the soft masking, doing the inversion, computing the new sample. And the faithfulness metric is basically simply uh, the difference between the classifier's probability for whatever the predicted class is uh, from the original sample to the new sample. If the components that we remove are true, encode something that's truly important for the classifier, the classifier's probability on x2 will drop. So we'll see ff of x to be positive. And just to ensure that the components that our algorithm identifies if they are indeed important, we have this random baseline where instead of uh, the components in LCX, we just randomly select the same number of components to remove. The results, there are results I'm showing here for 2 data sets. You'll find all the for the third one in the paper. So on the left, it's for ESC 50. So I'm reporting here the median faithfulness over the test data for different threshold values. The lower the threshold, the more the components you're removing. So we compare it with the random baseline for the lowest threshold. The essential takeaway is that even if you randomly remove these as many components, large number of components, there's still almost no change on the classifier's output. But with our method, at least we see a noticeable drop in probability. And it's the same case for this multi-label classification dataset, where we again report the median faithfulness. It's with a fixed threshold 0.1, but the results are separated for each class. So it's a median faithfulness for each class separately. The blue crosses, it's the random baseline, which is again, there's no impact on the classifier's output, but we see a lot more positive impact with our method. The second metric, I'll be rather quick, maybe a little bit quick with this, and it's more easier to understand, even though there are a lot of numbers. So the classification performance of a by design interpretable network. So the method that I described is this L2I by design. This L2I post hoc, it tabulates the performance of our interpreter that we trained for post hoc interpretation, not with the by design framework. This APNet is an audio prototypical network, which I think it's fairly common and one of the first ones. And there are 2 NMF based predictors. So these NMF based predictors perform a prediction in a somewhat similar fashion, in the sense what they do is they project the input X on the dictionary W, which is essentially the same as we use in our method. And then they have a linear layer on top of the time activations, on the average time activations. The difference between the second method is that it adapts the original dictionary W using the classification loss. So it has a better performance. The 2 key takeaways is that our method has better performance than all the interpretable baselines. And the base F accuracy denotes the accuracy of the original classifier f of x when it's trained just for classification, nothing else. So our performance is better than the interpretable baselines. On 2 out of 3 cases, it's somewhat close to the original classifier, but not it hasn't fully bridged the gap yet. And the one thing I find interesting is, especially compared to the NMF based baselines, that we have a very simple prediction structure. But the reason we have a better performance is that this NMF like interpretable structure is leveraging hidden representations of the classifier, which I think is the main reason for the better performance. Yeah. And just an obligatory illustration. So this is an example interpretation. I'll play an input audio which consists of 2 classes, a crying baby class and dog barking class. I hope everyone was able to hear that, because I don't know yet. I've shared my computer audio. But okay, this classifier was trained for multi-class classification, and it detects the presence of the crying baby class. So in the interpretation, we want to confirm, was it really the crying baby that led to the decision? So now I'll play the interpretation audio. So yeah, you can be assured that, okay, for this case, it's probably focusing on the right areas. Yeah. And so just to conclude, I basically presented a framework that can tackle both post hoc and by design interpretation problems for audio processing networks. It uses these NMF based representations to represent the audio objects for obtaining listenable interpretations. One thing that I find interesting about this framework is this idea of translating the representations, these deep neural network representations, to something to an NMF like representations. So from the hidden layers to this notion of time activations. And obviously, although I haven't worked on it for a long time now, if we were to build on this framework itself, one could obviously explore novel constraints that could be applied on the intermediate embedding or W, the dictionary. And one part that we haven't fully exploited is this concept representation part, because individual components here, uh, even though they are not the same as the original raw features, they are high level features of, of- through which we get the interpretations. But the individual component cannot represent very complex concepts. Probably sets of components, sets of spectral patterns could represent a concept, and this aspect we haven't yet explored. I don't know if I have more time.
Yeah, you're actually running out of time, so
Okay, so
yeah.
then I'll make this my as my last slide. So thanks for paying attention. And even if you didn't do, I can't do anything about it. You'll find further details about the project. I'll see how I can share the slides. And yeah, I'll also have the link for the project webpage. Yeah, thanks.
Thanks, Jayneel. So I think we have time for one question from the audience. Is there any question? Okay, I have one question actually.
Yeah.
So when using this approach, like if you go back to the diagram where you're presenting the approach, it seems like one of the possible, let's say, failure point
Yeah.
might be how well the theta network can actually mimic the classifier, right, based on limited information it has as input. Like, did you
Yeah.
try to elaborate on different architectural types for the theta network, or did you see that this is not indeed a problem, or?
So there are two aspects for this. Uh, so about the architecture of theta, we did some experiments, but I would say so the theta network has two parts. It will pool the activations in this hi of x, try to obtain a single vector, and there's a linear layer on top of it. I did experiment with the linear layer part, which I think changing it would improve the fidelity. The reason is that keeping this just a single linear layer, keeping that as straightforward, makes this estimation of importance very very easy. It probably can also be adapted for more complex type of theta. Uh, but yeah, I didn't consider that. I did consider trying different type of pooling functions. So instead of just average pooling, we did end up using attention based pooling. Uh, yeah, that's the extent of the experiments I tried. And yeah, the reason is that the estimation of importance becomes very easy if theta is simple. Um, the other aspect I wanted to highlight is that the the thing about fidelity can be helped to some extent if we're using the layers close to the output. So that certainly helps with the fidelity a lot. Although yeah, it's not perfect because this intermediate embedding itself is constrained through different losses and it has a very specific structure. But still, that part can help for some new data.
Okay, thanks a lot. Thanks a lot. Yeah, thanks. Let's maybe thank again Jayneel for his presentation.